mathematics. How much gold can you hold in an elephant's ear? When it's noon on the moon, then what time is it here? If you could count for a year, would you get to infinity or somewhere in that vicinity? When you choose how much postage to use, when you know what's the chance it will snow, when you bet and you end up in debt. Oh, try as you may, you just can't get away from mathematics.
Good morning, SCS students, and welcome back to another week. I hope you all enjoyed your Easter long weekend and that you were able to celebrate with some family, be it virtually or your own immediate family in your homes. I pray that it was a good time for you to just reflect on and to be blessed by the death and resurrection of our Lord Jesus Christ. As we get into today, I want to share with you a verse of the day today. The verse of the day today comes from John 13, verse 35, where it says, "By this everyone will know that you are my disciples, if you love one another." So the encouragement today for you is to love one another. I want you to think about ways in which you can practically love one another today. Maybe you can reach out by text or by a video chat or FaceTime or by sending a note to somebody or just by serving those around you. I pray that you would reflect on how you can do that, how you can practically love one another today. Grade 11s. For you, we're going to start today looking at electromagnetism. So on last week, Thursday, you read a little bit of section about magnetism, and we're just going to go over to the whiteboard. We're going to review a little bit of that, and then we're going to talk a little bit about just the beginnings of electromagnetism. So let's go on over to the whiteboard. All right, so again, on Thursday last week, you read about magnetism, and the biggest thing you should have gotten out of that was simply that there are magnetic fields that surround magnets, and that the magnetic field is similar in nature, almost exactly the same in nature to an electric field. That magnetic field is present around a magnetized material, regardless of whether there's another object in the presence of it or not. And the other big thing to remember is the direction of magnetic field lines, and it's important to remember that magnetic field lines run from the North Pole to the South Pole. And so if you're thinking of a bar magnet, we have a North Pole here and a South Pole here. The magnetic field lines leave the North Pole, come around, and enter the South Pole. So they are going in this direction. And of course, they do that multiple times around here. They leave the North Pole, they enter the South Pole. And if you were to bring a compass, what compasses do, compasses align themselves with the magnetic field. And so when you have a compass, it aligns with the magnetic field and it will point to the North Pole. Now you might say, what? That's opposite, because a compass will point to the North Pole. And if a compass was in this presence and it aligned itself with the magnetic field lines, it would in fact point toward the South Pole. Well, that is simply a case of, again, scientists back when they were discovering all these properties and not having all the technology that we've had in the years to come. And so what happens here is if you think of the Earth works like a bar magnet, and where we have our north geographic pole and our south geographic pole, magnetically those are reversed. And so at the geographic south pole is where we have our magnetic north field, and at the geographic north pole is where we have our south magnetic pole, and that gives us field lines then that surround the Earth going in this direction, right, going from north to south. And when we place a magnet, when we have a magnet in this or a compass in this magnetic field, it will align itself towards the north geographic pole. All right, electromagnetism is where we want to start today. And I'm going to say one thing today, and then I'm going to get you to do some reading in your textbook. No questions on it, just reading. And then tomorrow we're going to get into what happens when we have an electric field and a magnetic field, and they combine and interact, and what kind of forces are in play there. So the only thing I want to say today, and it's the most important point about electromagnetism, is that moving electric charges produce a magnetic field. So anytime an electric charge, an electron, a current, which is moving electrons, anytime we have a moving charged particle, that is creating a magnetic field. And that's the most important thing. If you realize that, what that means is that if we then take, and this is what we're going to be doing in the next few days, we're going to take moving electric charges and we're going to put them into magnetic fields and see what happens. And that's the whole basis of electromagnetism, is putting current into magnetic fields and creating what's called electromagnetism, which when we get into grade 12 physics will lead into things like Faraday rings and transformers and eddy currents and all these things that are used on a fairly regular basis, not in your daily life, but certainly by hydroelectric dams, by transporting electrical energy from those dams to the cities and to your homes. We need a lot of those things to make that happen. And so this year we're just looking at the very basics of it. We're going to look at what happens when we have charged particles in a magnetic field and what forces are present. So we're going to go with that starting tomorrow. For today, I want you to realize this statement, as it's a very important statement, and then I want you to do some reading in your textbook about what are called right-hand rules. Because if it produces a magnetic field, magnetic fields have direction. And so the right-hand rules that you're going to discover will, or as we'll read about, tell us the direction of the magnetic field that is being created by a moving charged particle. And so I'm going to get you to read them. Tomorrow we'll go over them and cover them. Remember to use your right hand, as it is a right-hand rule. I can count how many times that I've seen students using their left hand to try to answer a right-hand rule question. So make sure you use your right hand to do the question, or when you get to the questions, when you want to find directions. And but for today, read out of the textbook. You'll find those page numbers on Connect, but I'll say them here as well. I want you to read pages 648 to page 651 out of your textbook. And again, you're taking notes specifically of the right-hand rules for the direction of the magnetic field. All right, because again, we're going to look at forces, which is a vector, which means we need directions. And so try to understand from the reading what the right-hand rules are and what the directions of magnetic fields are around moving electric charges. That's it for today. Hope you have a great day, and we'll see you tomorrow where we'll look into this a little bit more.